As you can see from the title of this tutorial, this lesson is about average atomic mass and something we call isotopes. These two topics go hand in hand together because finding the average atomic mass of an element off the periodic table requires knowing what an isotope is and using values about these isotopes to get the average atomic mass. So, if we're going to discuss isotopes, I think we should start with a definition. An isotope, by definition, is an atom of the same element that has a different mass. Every element on the periodic table has isotopes. The decimal number that you see on the table, right, is not the mass of every single atom of that element on the entire planet. They call it the average atomic mass because certain atoms have different masses. Where does this difference in mass come from? It has to do with the number of neutrons they possess. So isotopes are created by the fact that atoms have varying numbers of neutrons. So it's due to varying number of neutrons. The number of protons in an element will never vary. The number of protons is what gives an element its identity. For instance, every atom of carbon has to possess 6 protons. Otherwise, it's not carbon any longer. If it has 7, it would then be nitrogen. The electrons can vary, but that doesn't change the mass because electrons are so light in comparison to protons and neutrons, the mass is unaffected when they are gained or when they are lost. Neutrons do not have to be constant. It is not a neutron that defines what an element is, but the neutron will affect its mass. So if we're going to look at things about isotopes, we wanted to discuss a terminology that you'll see with isotopes that is called hyphen notation. And hyphen notation was created to show that varying elements can have different numbers of neutrons. For instance, there are 3 different types of oxygen atoms. One oxygen atom has a mass of 16. One oxygen atom has an atomic mass of 17. And a third one, a different one, is an atomic mass of 18. So if we were going to look at these, what you need to understand is that the symbol over here is what tells us the element. So if I'm looking at O-18, this here is simply the nuclear symbol. And that tells me the number of protons. Oxygen's atomic number is 6, so it has, it's 8, so it has 8 protons. This number here is the mass number. And if you remember from learning how to calculate protons, neutrons, and electrons, the mass number is the protons plus the neutrons. So what happens is this. If I look at these 3 isotopes, O-16, O-17, and O-18, we could, just like we did before, figure out how many protons, neutrons, and electrons each of them has. if we did this, we would start with O16. O tells me it's oxygen. Oxygen's atomic number, which is our number of protons, is 8. The electrons always match the protons, so that will also be 8. And then remember, to get the neutrons, what we do is we take the mass number, which is listed for us, minus the protons. So this here would be 16 minus 8. This would also have 8 neutrons. The second isotope, O-17, we would do the same thing. The protons would be equal to the atomic number, which is going to be 8. The electrons will also match the atomic number, which is 8. But the neutrons, right, will now be a little bit different than they were before, because now I have a mass number of 17. And with a mass number of 17, it's 17 minus 8. This has 9 neutrons. So you can see the reason for the variance in the mass has to do with the fact that an atom of O17 has 9 neutrons instead of 8. No surprise here. Oxygen-18 would have 8 protons, 8 electrons, and now 18 minus 8, because the mass number was 18, which means it would have 10 neutrons. So what you can see is that isotopes are created because certain nuclei will carry additional or less neutrons than we would expect them to. Every single element on the table will have isotopes. How many they have can vary. An element like oxygen has 3. Hydrogen has 3, and hydrogen is one of the few that they all have different names. The hydrogen off the table is known as protium. The hydrogen that has an additional neutron is called deuterium, and the hydrogen that has a third particle in the nucleus, which gives it 2 neutrons, is called tritium. So what I want you to understand is, because there are different atoms, all of the same element, that average atomic mass off the table can't just be 16 or 17 or 18. It has to reflect all of the isotopes. So that's what we're going to look at next. We are going to talk about how do we calculate the average atomic mass. And remember, the average atomic mass is the decimal number on the table. So I said it relates to this idea of isotopes. So if I am going to calculate the average atomic mass, I need to account for each isotope. The catch to this is that the isotopes may or may not be equal in proportion. O16, O17, O18. It is not necessarily the case that 1/3 of the oxygen atoms have a mass of 16, a third have 17, and a third have 18. In fact, it's hardly ever that balanced. What you will find out is that O16 is about 99% of the oxygen atoms that we know of. So what has to happen is we not only have to account for the fact that there are multiple isotopes, we also have to reflect the number on the table to the percentage of that isotope in the world. So what happens is we do this. We take each isotope and we want to figure out how much that isotope contributes to the atomic mass. So what we do is take the percent abundance times the mass of that isotope. And that will get me how much of that isotope contributes to our average atomic mass. We have to do this for each isotope. Right? So what you'll have to understand is if we would have 2 isotopes, we would have 2% abundances times the mass of each of those isotopes, and those would each get me a number. Then, to get the average atomic mass, I simply add those numbers together. So we're going to take a look at an example or two, right, of this and show you how we get the average atomic mass of something on the table. So I'll leave that formula right there so we can refer back to it. Let's take a look at something off the table like copper. Now, I would have to give you some information. There is no way I would ever expect you to know the percent abundances or the mass of the isotopes. So I have it up here on my computer screen, right, but I'll list them up here for you so you can see what's going on. Copper has two isotopes. It has Cu-63 and Cu-64. So if I want to try to calculate the average atomic mass of copper, I need to account for both of these isotopes. So Cu-63, I would need the percent abundance times the mass of Cu-63 and Cu-64, the percent abundance times the mass of Cu-64. Remember, these are the mass numbers, so they're rounded. We need the exact mass. So, if you look up information about Cu-63, I could tell you its percent abundance is 69.17%. I can tell you that its mass of that is 62.929599. Now, the percent abundance was 69.17%, right? But whenever we do a calculation for the average atomic mass, the percent abundance is always expressed in decimal form. So the 69.17, you swing the decimal 2 to the left, and you get 0.6917. Doing the same thing for the Cu-64 isotope, we'll find that its percent abundance is 30.83%, so it becomes 0.3083 as a decimal. And an atom of Cu-64 weighs 64.927793. So what we'll do is we'll get what each of those isotopes contributes and then add them together. So you take out a calculator. We'll take our 0.6917 times 62.929599, and that tells me that this is 43.52843. And don't worry about significant figures for these calculations, simply get yourself a number. And for the bottom one, 0.3083 times 64.927793 gets me a mass of 20.0172385. And like I said, we're going to add those values together. So we will take 43.528403 plus 20.0172385 and get a value of 63.5456415. Sure enough, if you look in the box on the periodic table for copper, its number on the table, and I'll look up to the one we have here, is 63.54, and sure enough, 63.54 is what we got. And the reason for that is we account for the percent abundance times the mass of each isotope. The more percent an isotope is, the more this decimal reflects it. For instance, 70% almost was of 63, and 30% was of 64, which is almost a mass of 65. So take a look. The number more reflects the isotope's mass 63s. I'm going to give you the percent abundance and the masses of a different element. I want you to try the same thing, and I'll tell you what the final answer is, and you can see if you calculated it correctly. Let's take a look at something like carbon. Carbon has 3 isotopes, C-12, C-13, C-14. Carbon's 12's percent abundance is 98.9% abundance, and the mass of it is 12 exactly. Remember, change this to a decimal form. Carbon 13's percent abundance is 1.1%, and its mass is 13.003355. And lastly, Cu14 is 0.00001%, and carbon 14's mass is 14.0003. 242. And that's 0.003242. So go ahead and get what you believe the mass of that to be. Add them all up, and sure enough, if you do it correctly, you should get a number really close to what you see on the periodic table, which is a value of 12.01. If you have any questions about this, please feel free to stop in and have some help, but I hope this cleared things up for you on average atomic mass.